Good morning, Doctor. We are members of Group 6 of Optic assignment. First, let me introduce myself. My name is Wong Ping Soon, matrix number 229724.
My name is Fong Ming Xuan, matrix number 229556.
My name is Wu Yun Heng, matrix number 228599.
My name is Ashim Long bin Adam Long and my matrix number is 228982.
The optical instrument that we chose is spectrometer. There are four principles of operation of spectrometer, or in simple, I say as four steps that how spectrometer function, which is one, light intake and collimation, two, dispersion, three, focusing and aberration control, and the last, which is detection and electromagnetic theory. First step on how spectrometer work is light intake and collimation. At the light entry, light enter through a narrow slit. The slit acts like a gatekeeper, controlling the beam width to ensure only focused light proceed. By using the reflection principle, the collimating mirror then reflects incoming light. According to the law of refraction, the angle of incident equals to the angle of reflection. This converts the diverging ray into perfectly parallel path. While by using geometry optics, the precision alignment of the mirror ensure the minimal path error. While parallel ray, they eliminate distortion, critical for accurate wavelength measurement.
Step 2 is wavelength separation, and there are two main methods to achieve this. One, using a prism. Second, by using diffraction grating. First, the prism method relies on refraction, which is the bending of light as it enters and exits a material like glass. This bending causes light to spread out into its component colors. According to the dispersion principle, different wavelengths of light bend by different amounts. For example, blue light, which has a shorter wavelength, bends more than red light, which has a longer wavelength. The shorter the wavelength, the higher the refractive index. This creates a visible spectrum. The relationship governing this behavior is described by Snell's law, which states n1 multiplied by sin theta 1 equals to n2 multiplied by sin theta 2. The second method uses a diffraction grating, which contains thousands of tiny grooves etched closely together. Instead of bending light, this method separates it through interference. Each groove causes the incoming light waves to diffract and overlap, reinforcing or cancelling each other depending on their wavelengths. This process follows the principle of geometrical optics, and the condition for constructive interference is given by the equation d sin theta equals to m lambda, where d is the spacing between grooves, theta is the diffraction angle, m is the diffraction order, and lambda is the wavelength. In both methods, the result is the same: spatial separation of wavelengths, or the splitting of light into its constituent colors.
In step 3, image formation occurs as a convex lens focuses the spectrum on the detector. According to the principle of geometric optics, lenses convert incoming rays of light by means of their curvature. The focal length of the lens determines how much the light is magnified. However, imperfect lenses introduce a challenge known as chromatic aberration, where different wavelengths of light are reflected by different amounts, resulting in color blurring.
Hi, my name is Yun Heng, and today I'll be talking about the detection and electromagnetic theory of a spectrometer. So the most important component in an spectrometer is the charge coupled device, or CCD. What this essentially is it is a device that whenever you deposit some photon on it, it's going to then emit some electron out of it that we're then able to process and convert it into a more visual data. So the way this works is that we are incorporating this formula, which is E equals to Planck's constant times speed divided by the wavelength. So each of these individual wafers are then going to be designed to have a specific wavelength of light that they're able to capture and convert it to some kind of data. So next, inside a spectrometer, we're going to have a diffraction grating, which is this thing right here. So what it's going to do is basically whenever you have white light that is incident upon your diffraction grating, it's going to diffract into multiple different colors. And because it is a diffraction grating with multiple slits, the different lights are going to intersect and is going to have some sort of superposition, and then interference is going to occur. So you're going to have certain parts that are constructive and certain parts that are destructive, right? So you have these blurred out parts that are destructive, then you're going to have the more concentrated and bright parts as a constructive interference. Okay, so this is what the diffraction grating is going to look like in your uh in the spectrometer. So the way this whole thing is going to work is that you're going to have some kind of white light that is incident here, and then it's going to be diffracted into multiple colors. Then let's say, assuming today that we have a sample of hydrogen gas, then the gas is then going to absorb some of that photon energy, and then it's going to um, release some photo electrons, which are then captured by your CCD and converted into some kind of spectrum, which can then be further processed into something like the hydrogen spectrum. Thank you.
In just 4 steps, collimate, disperse, focus, and detect, the spectrometer unlocks the universe light secret. From starlight to pollution tracking, it turns physics into discovery. Thanks for watching. That's all from us.